All right, thank you. I appreciate the opportunity to brief the NCAB and the BSA on the NCI Cancer Genomics Cloud Pilots concept. Before we actually get into the meat of the concept, part of the explanation for why, we have to go back to the question of how it is that computational analysis on biological data has historically been done. So if I'm going to start with what I'll sort of call the standard model of computational analysis, which I've cartooned up here. This is for analyzing data that an institution or a laboratory ultimately winds up generating within their own institution, as well as potentially data that comes from other institutions. And the basic idea is that typically you wind up setting up a set of local storage and compute resources that you're going to have put your data on. You bring your locally developed data, put it on there. Then you go out to public data repositories where there is information that you want to integrate with that information or make part of your analysis, obtain it through network download, do some kind of local aggregation within your local computing repository. And then use either a set of locally developed software or, in some cases, publicly available software from a variety of sources to do your analysis. And this has been, in fact, a very successful model for doing biomedical computation for a long period of time. However, there are a number of stressors to this model that are making this model increasingly obsolete, and at some level it may actually be that it already has stressed to the point where it is obsolete. One of these things is clearly the fact that next-generation DNA sequence technology has given us a wealth of new information. This is the growth of the sequence read archive from the European Nucleotide Archive. I borrowed this from the EBI website. And what you can see is that between 2006 and 2013, this is a logarithmic graph. On the left, you have sequences. On the right, you have bases. It's gone from about 1 million sequences to something on the order of 4.1 trillion in that span, and from about 100 million bases to something on the order of 520 trillion bases. As a scientist, I'm very excited about this. As a chief information officer, I'm absolutely terrified. A little closer to home, if we take a look at the sequence data that's being generated by the Cancer Genome Atlas program, I will point out that in the total expected size of the sequence data that's going to be generated from TCGA, we are here. So we've approximately 1/2 of a petabyte, that's 500,000 gigabytes. But by the end of the program, at the end of fiscal 2014, so September of 2014, we fully expect to have 2.5 million gigabytes, or 2.5 petabytes, of DNA sequence that's going to have come from this single project, the Cancer Genome Atlas. Another complication that we have here is that, in fact, we don't just have sequence, okay? Obviously, there is a large number of orthogonal data types, many of which would have, until not all that long ago, been considered big data themselves, which are now, of course, also being generated on these large numbers of samples and are being joined to these large amounts of DNA sequence data. Obviously, this includes expression data, the sequence data itself, copy number, genome rearrangements, epigenetics, clinical annotations, images, etc. And generally speaking, the higher the dimensionality of the computational problem, which in this case is at some levels the numbers of data types that you're dealing with, obviously the more complex the computational problem if you want to try and analyze across those multiple dimensions at the same time. So this begs the question of that model that I showed you at the beginning. What has already been stressed? Well, let's take a look at the 2.5 petabyte TCGA data set. And the argument that I'm going to profess is they're already all broken. To store and protect 2.5 petabytes of data is approximately $2 million a year. That's just keeping a copy of the data. And that's actually a very, very cautious assumption, assuming, in fact, that you already have access to a petascale environment, and what you're doing is adding a marginal 2.5 petabytes, as opposed to if you need to bulk up from a much smaller scale up to 2.5 petabytes. For those of you who are curious, that's 6.6 cents per gigabyte per month, of which about 2.2 cents is amortized acquisition costs, and almost all of the rest is data protection, tapes, staff to maintain the things, power, cooling, software licenses, etc., all the things that you actually need but that aren't included in the cost of the arrays to maintain things on petascale. If you were to try and download that data, well, TCGA is 2.5 petabytes, or it's going to be. That's 20 million gigabits for those of you who prefer to convert into network speeds. If you had a dedicated 10 gigabit per second line and you didn't have to share it and you could get maximum throughput, which is impossible, it would take 23 days to download that data each. Okay, so that if, of course, 5 or 10 institutions want to try and share this data, obviously the download speed reduces. Even if you had a 10 gigabit per second line, network latency itself means that you're unlikely to exceed 1 to 3 gigabits per second, and therefore that you're talking somewhere probably between 180 and 250 days. And again, that's assuming at no point it has to cross a 1 megabit per second line or that you're sharing this line with anyone else. Finally, the size plus the dimensionality translates ultimately into extremely high computational requirements, and that these things grow very, very fast. So from both a practicality standpoint, can you even get the data? And from a cost standpoint, the notion that we could replicate this kind of capacity at 64 cancer centers or at every individual research lab is at a point where it simply is not really a very viable option. I'll also point out that I priced, just for the heck of it, what the download charges from a large unnamed cloud provider would be to download, the network charges to download the current half a petabyte TCGA data set, and the answer was $25,000. So obviously it's not going to scale completely linearly. Bandwidth gets a little cheaper as you use more of it, but nonetheless, just the bandwidth charges associated with moving these things from point A to point B is in fact a major, major problem, even at our current scale.
So just to clarify, these are all the raw BAM files, right?
Yes.
Not the post-analyzed variant
No,
files.
this is all the raw BAM files.
So there is some intermediate.
There is a smaller data set, absolutely.
Yeah.
That said, we have the problem that I've just described is dealing with a data set that does not at this point exist. Right? We have a half a petabyte data set, and the question became that we wanted to ask was, well, have we again already passed the point where this model that we've been using is a problem? And so a letter was sent to all NCI grantees as well as all intramural NCI scientists from Dr. Varmus, myself, and Steve Chanik and Lou Stout in their capacity as acting co-directors of the Center for Cancer Genomics, asking 3 questions about situations where limitations in information technology were preventing you from carrying out certain types of high-value research, or where the limitations, while they're not preventing it, are slowing the pace of discovery. Also, experience with high-performance computing, including clouds and commodity clouds, as well as dedicated high-performance environments. And then a set of metrics could be used to assess if we were to build a cloud, which I'm going to talk about in a minute, how we can measure success. We received 68 responses to this letter. Many of them were sort of institutional responses rather than individual investigators, although obviously there were individual investigators as well. On the whole, actually, it was these were a very well thought out set of responses. 29 universities, 20 government scientists, 13 research institutions, and 5 companies. There were 6 major themes that came out during those responses. I want to focus for a moment on a couple, on the 2 of them, the data access and the computing capacity. And what seems to have become clear is that long before we hit the 2.5 petabyte scale that's going to be the end of the 2014 TCGA data set, there were already significant problems with data access. Many groups reported that it was impractical for research institutions to download and store common genomic data sets such as TCGA, that it was beyond their data management capacity, and frankly, individual investigators were struggling managing their own local data without attempting to also mix in this very large public data set. Downloading and transferring the data was considered a critical limitation. A number of respondents stated that it was, quote, not worth it to spend days downloading this data to do an analysis. In terms of computing capacity, again, most researchers argued that they simply did not have access to the kinds of resources that were necessary to analyze data on this scale. And a point that is going to come up that I will mention, I want to bring in, discuss a bit later, but I'll mention it now, is that many of them were arguing that not only is the problem of providing high-performance computing difficult, but the fact that many different types of analysis require different types of high-performance computing environments was a problem, in the sense that they would then have to potentially create multiple high-performance computing environments in order to answer these multiple different kinds of questions that they wanted to ask. So, as you might speculate, we're proposing an alternative to the standard model, something that we're calling a biomedical cloud. And the biomedical cloud that we are proposing here is fundamentally a computing environment, and I'm calling it a cloud for convenience, even though that's an incredibly overused word, that provides co-located, whether it's physically or logically, computing and storage, and that it's preloaded with public NCI data, so that investigators would bring local data and analysis tools to the cloud, do their computation there, and get the results back, instead of trying to take the large public data sets, take it to their local institutions, and do the computations there. We think that, in fact, such a cloud has the potential to democratize access to public data, since this would be a resource that could be made available to scientists and researchers based on the merit of the investigation that they ultimately want to do, rather than necessarily the wealth of their institution. So let me spend just a moment and dig a little deeper into a logical view of the cloud and what it is that we're actually talking about building here. So clearly we have computational capacity. These are servers, the kinds of things that you need to be able to do computations. And on those servers would run a variety of applications. One of the things I want to point out is that end users are not going to interact directly with the cloud. They're going to interact with an application that runs on the cloud, much in the same way that on your iPhone, you don't interact directly with the inner workings of the iPhone. You interact with a series of applications that run on that platform. In addition, we would provide obviously storage that would be co-located, both for core data, the stuff that is the NCI public data, and would come from something that's we're being called a data commons. I'll have more to say about that in a moment, as well as local user data, so that it can be aggregated and used in the computations. Finally, in the center here, this little box labeled API, that stands for Application Programming Interface. Okay, this is what the programs that people write interface with, so that they can get access to the core data, they can get access to the computational capacity, much in the same way that the operating system on your iPhone, the iOS, allows you to have access to the resources of the iPhone, the computational capacity, the storage, the data, etc. In effect, we would have a whole series of applications that would run and would use this application programming interface for data access, security, and resource access. And I should point out also that this is what an engineer would call a logical view. How this is actually implemented is not necessarily going to be you're going to have a storage array here and a user array here and then some kind of computational capacity elsewhere. Okay, from an engineering standpoint, it likely is going to be arrayed quite differently, but this is how the parts are there and how they flow from point A to point B. So how does this cloud fit into sort of a broader context of NCI investments in genomics? Well, obviously we have a series of data providers that are part of TCGA and other projects, Target, CGCI, etc. Ultimately, this data is fed into a data coordinating center that does quality assurance, quality control, validation, data aggregation, and then ultimately then creates an authoritative NCI reference data set. This data set is supplied to the community through this NCI Genomic Data Commons that I mentioned, and it also is supplied by the Data Coordinating Center to the NCI clouds. An end user that wants to retrieve data or search and identify a subset of the data goes to the Genomic Data Commons. It's obviously the authoritative reference data set. If you want to perform high performance computing and analysis, you go to the cloud. So that at the end of the day, what we have here are two distinct entities that provide two distinct services to the community. One that provides access to the data for those who want to download and obtain local copies. One that provides access to high-performance computing on that data to the community that wants to do analytics. So here we have our cloud. At this point, though, it's probably a bit premature to go straight to the sort of 5 to 20 petabyte scale cloud that probably is what you actually need for the next 3 to 5 years, assuming that we continue doing large-scale genomics in the cancer research community. Instead, we are proposing to support the development of 3 prototype clouds at a scale of approximately 2.5 petabytes worth of core data, enough to give the NCI compute capacity for the existing data that we expect to have at the end of the TCGA program at the end of fiscal 14. Our idea would be to put out a broad agency announcement. I'll tell you a little more about that in a bit. Select up to 3 proposals for pilot scale development, that's 2.5 petabytes. At the end of that period, we would conduct a set of evaluations, and again, I'll talk more about the evaluations a little later, but we would assess which cloud designs were effective for what types of questions so that we could decide how we want to proceed with building out a larger infrastructure to ensure that the community has the computing resources that it requires. One thing I do want to point out is that at the end of these pilot phases, these clouds would represent usable cloud computing infrastructure for cancer research at a 2.5 petabyte scale, again, for the TCGA scale. And going back to the responses to that informal request for information, one of the comments that was made was that various architectures, various types of computing infrastructures are good for certain types of calculations. And so one of the things that I think by doing these pilots, we would wind up with a broad array of computational capacity that would be available for the cancer research community. In addition, we intend to operate this as a consortium so that what is learned from one cloud can ultimately wind up informing the other. And this consortium would include the NCI Genomic Data Commons, obviously the entity that's going to be creating a core data set, which in this case would be the DNA and RNA-seq plus the clinical annotations that would be going to all the clouds. That would give us an opportunity to do some level of both pan-can analyses as well as providing some way of evaluating apples to apples. But at the same time, the expectation is that a successful offer is going to also support at least one other non-sort of core data type. So you can imagine one of the clouds might support epigenetics, one might support imaging, one might support copy number, whatnot, so that we wind up at the end of this pilot period with these 3 clouds producing a broad array of capabilities that can be used to analyze a very large fraction of the totality of the data types that are going to be coming out of TCGA. In terms of schedule, we've sort of broken it into 4 stages. An initial selection phase, which would be announcement responses. Because this is a broad agency announcement, it would be peer-reviewed instead of having a conventional FAR-based, the Federal Acquisitions Regulations-based internal review. Contract negotiations and award. This would be followed by a 3-month design phase where we would certainly expect that in the process of responding to the broad agency announcement, an initial design would come in. This would give an initial 3 months to flesh out the designs, followed by a 12-month construction phase during which they would develop the cloud, implement the cloud, develop the API, etc. And finally, an evaluation phase of 6 months where the clouds would be provided to researchers and we would conduct both NCI and community-based evaluations. So just a few considerations on this. Initially, first, design and intellectual property. We obviously want to consider all possible designs, whether they're using commodity cloud technology or implementations using dedicated hardware. The important thing is the design itself has to be released under a non-viral open source license because we want anyone in academic, commercial, whatever, to be able to take those designs and implement their own clouds if they're inclined, or build derivative works from this. And therefore we would assume the commercial products would be okay as long as they're available under standard commercial terms and don't inhibit the IP rights that are needed. Another consideration is extensibility and interoperability. Obviously, they're going to be focusing on a set of core data types plus some, but these designs absolutely have to be capable of extending to additional data types without a major refactoring of the existing system, or we haven't gained much. And the cloud designs need to be interoperable to the maximum degree possible. I realize that's a bit of a weasel word, and I'm going to try and put a little bit of more certainty around it. Obviously, that means they're going to need to use the data standards defined by the Data Coordinating Center and the Data Commons. They're going to ultimately, we hope, support a common core application programming interface, but that's going to evolve over time along with the consortium, much as the early web started out with a very small core set of interfaces, and then as groups developed new capabilities, they wound up and had code, they got incorporated into the standards. I think we need to, and given also the fact that these are going to have different data types in them, they're not going to be 100% interoperable. You're not going to be able to take a program from one cloud and with no changes at all move it to another cloud. That said, I think it's important that we don't let the perfect become the enemy of the good enough. And I think that we can do interoperability that is good enough. In terms of scalability and sustainability, they have to be designed to support an expansion, I think, of up to 100-fold in the areas of data size and usage. And one of the things that we're going to expect from these groups is a sustainment plan so that we can do cost assessments for operating at current scale, 10 and 100-fold increases. And I'll point out that the operational costs in these modes are going to vary a lot depending on the technical solutions. Commodity clouds have low capital costs but high operating, and vice versa for dedicated hardware. We're planning on doing this through a broad agency announcement. It's a very flexible mechanism for doing contracts. In this case, you put out a very broad set of requirements and allow groups to respond. And instead of having a single contract that you would make 3 awards to, the contracts that go to the individual groups are dictated by the response. It also allows for peer review during the selection process, which I think is a better way of doing it than having an internal NCI review group. Clearly, we're going to be doing some NCI testing, but we also want to make sure we do some community-based testing. At the end of the day, which of these systems, which are going to be made available, do the community members like using? And the idea would be to use challenge.gov or topcoder type contests to incentivize use. Plus, of course, the BD2K U54 centers are going to need computational capacity to run the new analytics systems that they're going to be developing, and this kind of infrastructure is perfect for that. I do want to point out we don't plan to expand the clouds until they're reviewed by appropriate groups. The contracts are likely to end at the end of the evaluation phase, and will require, to continue on, would require a separate contracting action by the NCI. I'd like to just finish up on two last items. One about possible models for long-term support. Obviously, we have institutions that are going to be interested in using these clouds. Some way has to be found to make them available. The obvious sort of model, first model is an NCI-funded model. We choose the clouds that turned out to be successful. We continue funding them to expand as new data comes online, and they're made available to these organizations through some mechanism yet to be determined. An alternative model is what I'll call the institutional consortium model. Right? You can imagine the University of California system, or I guess the big 1-0s, now creating a consortial instance of a cloud that works for them, using resources pooled from those organizations, or individual institutions might decide to build a cloud if they have sufficient resources. A third option, frankly, is a commercial fee-for-service model. The idea is to make this available. It's quite possible that existing cloud providers would conclude this is a viable solution, a viable business model, and make it available on a fee-for-service basis. My suspicion, of course, is that we'll probably wind up with some kind of hybrid model that includes NCI-funded ones as well as consortial ones, and potentially some commercial ones as well. Okay, and then This didn't. Okay. Well, just a brief comment on operations and modernization. You know, if we go in with 3 clouds, there's a couple of ways that this sort of could wind up ending. We may decide that one of the clouds simply didn't meet our standards, and we decide that we're going to cut our losses with that one and terminate it. On the other hand, ones that we think work, we're going to want to have in steady state operations in subsequent years, with the notion that over time we would likely expand these to add additional data types, additional capabilities in terms of computation and storage, so that they can then continue to operate into the future. In terms of cost estimate, we anticipate design and implementation cost estimates per cloud of $3 to $5 million, as well as a $500,000 per cloud pilot for operations. Design and implementation in 14, evaluation in 15. Operational phases, again, we're estimating somewhere on the order of $3 to $5 million per cloud in FY16 and beyond. These estimates are varying quite widely due to the large number of options for the ways that they could be implemented, and I think we won't really have very solid operational phase assessments until we actually have a cloud and find out how much it cost. So some brief acknowledgements, some folks at CBIT who've been working on this, and also I'd like to express my gratitude to Barbara Wold, Lou Stout, and Steve Chanek from CCG, who've been very active in preparing this as well. I'm happy to take questions.
Thank you, George. Let's hear from the reviewers first and then have some discussion. Andrea, do you want to start?
So obviously, this is not something that we should discuss whether we need or not. We know we need it, and right now it has been dramatically sort of limiting in terms of what we can actually do at individual institution because of the tremendous download times that we're experiencing. There are even situations where, especially for centers that have a large number of computational investigators, where everybody downloads their own private version of TCGA, and it's creating tremendous demands on the institution that cannot be addressed. So, so obviously, I'm extremely supportive of this type of proposal. I do have some recommendations. The first one is that when you think about something on this scale, I think it's extremely difficult, especially if you want to accomplish it in the context of a cost recovery model rather than a commercial model, to ramp things up and ramp things down on the spot. And so, for me, the idea that we're going to do this on a 3 plus 12 plus 6 month time frame is a little, is difficult. It's going to be very challenging. So, for instance, what are the institutions going to do while the evaluation phase is in progress, and I think that is something that we need to keep in mind. So I would recommend, for instance, that we think about extending this to basically a 3-year program, with the final phase acting as the bridge between the end of the actual implementation phase and the end of the evaluation phase by third parties. This also allows sort of a more staggered model where you can actually start implementing and developing things that are relatively easier to afford, like, for instance, just centralizing the model. And then you can sort of delay a little bit. The second thing is that I think it would be great to have scientific goals that set the development of these resources. I think that this has been also my leitmotif also when I review CA Big, that in fact, so for instance, one thing that I would recommend is that each one of the pilot centers demonstrates having at least 3 driving biological projects that are set by institutions that they will collaborate with, and that have essentially what are the scientific problems that could not be solved without access to this type of infrastructure. I think that would greatly sort of simplify the evaluation process by seeing how this is actually impacting science. The final thing that I want to say is that the API model is the area where I would actually recommend not devoting each individual pilot to developing their own API. I would say that the 3 pilots should actually put forward a committee that develops a common API, because otherwise it's going to be very difficult to manage. But with these limitations, I think I'm extraordinarily supportive of the proposal.
Yeah, so one of the, going back to the driving scientific question, we collected a list of, from the responses of use cases, scientific questions that ultimately the investigators who responded wanted to have answered, and we're in the process of putting that up on idea scale so that investigators out in the research community can vote for the ones that they view as the most pressing. That will then be part of the ultimate broad agency announcement.
Yeah, I mean, honestly, I would not limit that only to those simply because the set of responders to some extent may have been biased. Some people were participating in more direct or indirect ways to the process. And so I think that allowing the pilot, whoever puts forward a proposal for pilots, to actually justify why certain scientific questions are currently impossible to manage with the current infrastructure and why they are important is something that can be left then to the reviewers to decide whether they're hitting the nail on the spot or not. But certainly it would be great to have guidance from those because some of them may be obviously reflected into those models.
Right. The thing with the API is probably going to also be driven to some extent by the degree of overlap of the common API is going to be driven to some extent by the degree of overlap of the types of data that are in each of the clouds and the specific types of analytics that it's optimized to perform. So that, for instance, we've heard a number of groups talking about wanting to do network analysis using graph theory. Clearly, that's likely to be a fairly specialized portion of any kind of interface that's made available to those systems. So, but I agree that to the extent that you can manage the core points, that's really going to be quite useful.
Yeah, no. So I'm not saying that each individual center should not have their own specific topical problems. What I'm saying is that it would be better if from the beginning we inform the centers that the API component has to be developed as a group application. And I've seen many of the networks are doing the same thing, including TCGA, sure, CTD Square, et cetera. So I think that basically saying, you'll have to put forward, candidate individual that will participate to a global committee to get API formally approved so that at least we know that we're all the same. Yeah. So something of that sort.
Okay, let's hear from the other reviewers. Lincoln Stein.
Sure. So let me start by saying I really welcome this this concept. People like me in the genome informatics community have been watching with great trepidation as the data has enlarged to the point where we see this event horizon coming towards us, where data will eventually go in and will never be able to be retrieved. I want to I just want to address a question which might be coming up in some people's minds of why it's important to have access to the raw data at all. Why can't we just download lists of the called somatic mutations, which are several orders of magnitude smaller than the raw data? And my answer is to look back at the history of GEO, which a decade ago established standards for depositing the raw microarray data with associated metadata into a community database, a resource that anyone could draw on. GEO has inspired thousands of papers in which people have taken disparate data sets deposited by different groups, combined them in ways that were very creative, which no one was expecting at the time they generated the data, and come up with great biological intuitions, ranging from regulatory networks to networks of related diseases, and in the process developed a greatly advanced science of normalization and analysis of microarray data. And without access to that raw data, if we had instead just deposited lists of up and down regulated genes, none of that would have been possible. So we don't know what all the applications that these raw data are going to be put to, but I know that there is a great deal of exciting findings that's hidden inside that data, and we won't be able to know what it is until some years go by and people are allowed to use it creatively. In order to use that data, we need to have access to the full data sets to be able to integrate multiple data sets, to work with it creatively, to have a low activation energy such that the bright graduate student can go in to the cloud facility of the future and start working with the data without first having to go to the university and say, I need 20 petabytes of storage. It'll take 2 years to download because I've got a nice little idea I want to try out. That's not going to work. So turning to the specifics of the proposal, I did talk with George and his team about it last week, and I find it to be kind of a very well thought out proposal. The particular things I like about it are that it is technology and architecture agnostic. It's really very broadly framed to allow for a variety of cloud solutions. I actually like the fact that they're putting they're putting some of the onus on suggesting use cases on the submitting groups. They're not creating a set of use cases in advance and asking them to be satisfied, but allowing the groups to think broadly and then to evaluate them by peer review. And I do like the timing. It is very aggressive, as Andreas had noted, and I think that is a risk. But it does tie in very nicely with what's going on in the academic community and commercial communities with the Global Alliance, which is seeking just around this time to identify partners to develop the APIs for cloud biomedical computing and to implement them. And so these, this pilot could in many ways be the test cases for the emerging global alliance. Finally, in terms of, I'll just have to disagree with Andrea on the topic of API. I think that if there's a phase in which you ask everyone to agree on a common API beforehand and then implement it, that is a kind of a recipe for delay and disagreement and ultimately the emergence of a mediocre product. I feel that a better approach is the one that was taken during the development of the network protocols of the Internet, where groups were, made a proposal and had to implement a solution to that proposal in order to submit a request for comments. And there was a bit of a free-for-all, but the best implementations won largely by people voting with their feet. In this case, there will be multiple pilot programs. Real-life researchers will be able to access it, spin its wheels, kick the tires, and ultimately they'll make the decision of which systems they like the best.
So I'm going to suggest that there's...
So that's the end of my comments.
Thank you, Lincoln. I'm sure many details to be discussed, and this probably isn't the group to debate the merits of various API strategies to begin with. Arul, any additional comments?
I too agree that this is a much-needed effort, especially since the NCI has spent millions of dollars on TCGA, and the average cancer biologist really can't tap into that. I mean, it's basically sitting dormant, so I think this is really a needed effort. My lab in itself has spent quite a bit of time and effort in downloading a good component of TCGA, and if you scale that out to many different labs across the country, that's a tremendous sort of duplication of efforts. So I'm highly supportive of this proposal. Just some procedural issues. I guess one aspect is why sort of carry this out with 3 pilots? Not that I'm suggesting to do this, but one could argue, why doesn't the NCI just take on this effort itself and support this? Or I guess what's the rationale for doing 3 pilots? Is it really some sort of bake-off between the clouds, or is it really looking for complementary clouds that might come together to being the end solution? I think just moving forward, it's unclear whether academics at individual institutions or even industry will be able to sort of support this maybe beyond the pilot stage. I think is the intent that the NCI would take over after the pilot phase to sort of support this over time. I think that's certainly something that you need to consider. And then the other aspect is that not only has the NCI generated a lot of data, there's a tremendous amount of data being generated by the International Genomics Consortium, non-TCGA supported efforts, just because the cost of sequencing has come down to a point where This is going to be prolific in terms of the types of data that average clinical investigators or biologists are going to generate. Is this effort going to sort of take on the world's cancer genomic data and make it accessible to the community, or is it only the TCGA and the target effort? The last comment that I'd like to make is certainly this cloud pilot will have utility outside of cancer. Have you really thought about really leveraging this across other human diseases, potentially getting co-investment from other institutes? I mean, certainly this pilot project will have utility in the context of diabetes and neurodegenerative disorders and so forth.
Want to address that, George or Harold?
I might just say one word about another effort on the NIH campus called Big Data 2K that is being led by a group chaired by Eric Green. And Eric is going to be coming to our retreat to talk about this very issue. Right now, I'm much more concerned with the issues you raised earlier. That is, are we going to be supporting one of these a little later on? Will one of these entities become an operating entity within the global alliance, whenever that appears? And so I think there are a lot of uncertainties here about the outcome of building a successful cloud within this pilot. But I do think it's better to bring in the world's expertise by advertising this and asking for competition, as opposed to having the NCI say we'll take it on.
Right, and I think the key thing is the only thing I would add there is that the notion of the three pilots acting in a consortium is to be complementary. While we are going to evaluate them all at the end, and some will be good for some things and some will be good for others, it's not to have a bake-off. It's to wind up with what the cancer research community ultimately winds up needing to do its job.
Right, but so I just wanted to follow that up, because do you end up in a situation where you're now forced to perpetually fund the three different centers instead of one cloud? That's one question. The second is, I was very excited about this because I fully agree, this is a massive problem, and sending the applications to where the data is the only solution. But I just assumed this was going to be Amazon, Google, or Microsoft, or
not necessarily. So let me.
And so I'm a little worried about that Amazon and Google weren't like part of the discussion we just heard.
So let me just go ahead and let me start with the first question, which is, if you read through the literature now, you know, Dave Hausler was at a precision medicine meeting here not all that long ago. I don't believe that a single cloud someplace is going to necessarily be sufficient to meet the needs of the totality of the cancer research community, no matter what. Now, whether in the long term you wind up with multiple instances of one cloud, or you wind up with one instance of one cloud and two instances of the other, you know, I'm not sure. As far as whether Amazon and Google, well, Amazon or Google may actually be able to come up with a good response, but again, you know, I think what we're trying to echo Lincoln, we're trying at the moment here to be technology agnostic. Maybe those commodity clouds make sense, maybe they don't. You know, I think that they would need to put in a response as anyone else would.
Yeah, so this is a little bit above my pay grade as far as an engineering and computational problem. But I would say that I thought it was a beautifully written proposal, really lucid. I really like the idea of going out to the user community and getting input and feedback. I think it's really important that for regular biologists who are not computational biologists, having interfaces that will allow people to get onto the cloud and use the data in a meaningful way would be really valuable. And I just have some mixed feelings about Andrea's suggestion that this be tied to trying to solve scientific problems. Because I just think the informatics problem is daunting enough that I want the groups to just focus. My bias would be to have the groups really focus on, you know, building a platform that really facilitated analysis. I can understand Andrea's point that if you have a problem in front of you and you're trying to solve it, it'll help inform your design. But I think the key thing here is to design the platform rather than to start solving scientific problems.
Comment briefly, I mean, George could do this too. When we thought about how to set this competition up, we were very clear that we wanted those who were going to be competing to have some sense of what kinds of questions the users would want to have answered. So when we put out the RFI, we said, tell us, what kinds of questions you find difficult to deal with now, and what would you want a successful cloud to be able to help you answer. So we're not asking people to go out and solve biological problems. We're asking them to be sure that when it comes time to assess the products that have been made into this pilot, that they're responsive to the kinds of questions people already have on their minds.
I think the price tag is way too low. I mean, I just can't imagine. I'm going to tell you, even for a pilot, we've been trying, at UCSF, we've been trying to convert to a new electronic medical record system, and we spend hundreds of millions of dollars. And when you showed the example with scans and MRs and stuff like that in there, and then we have a separate electronic medical record system called Mosaic, which we use for radiation stuff. These systems don't talk to each other. And I can tell you that this reminds me of the Bay Bridge that we're building. They said it was going to cost $1 billion, and now it's cost $6 billion, and it's faulty because the bolts that are used to hold the thing together are fundamentally flawed. I think this is a very, very important project that we need to have the capacity to store this data, but this is offering a Band-Aid for a serious medical problem, and it needs to be way more money involved in it in order to get serious people to really approach this problem appropriately.
So if I may, just one thing with there. In some ways, an electronic medical, having dealt with both research systems and electronic and systems that at the end of the day are associated with care, an electronic medical record in its own way is a more complex problem than we're actually trying to resolve here. Number one, an EMR is a regulated system, which means there is an enormous overhead associated with that regulated system. It's broadly deployed. It has thousands of users. It has to do hundreds of different kinds of things at the same time. I'm not saying that, we hope that that's this is, we believe, a reasonable estimate to do these pilots, but again, EMRs are a different kettle of fish. Lincoln looks like he has a comment there on that as well. So, briefly.
I would just say that there are a number of institutions who are building genomic clouds now that are in the position to build pilots for about the budget that you've given.
Okay. Ethan, did you have a... No?
Yes, thank you. Sorry. I was busy eating my chips over here. My afternoon snack time. Thanks. I thought it was a strong proposal. I just wanted to put in a plug that in population science research, we are confronting a similar issue with enormous data sets, particularly from large repositories of linked claims that pose similar problems in analytics. There are issues of privacy and security there that may be different, but I've seen at multiple institutions a pressing need because we have rapidly outgrown our storage and analytic capacity.
Jeff Drebin.
I would raise just the question of, do you really want to do 3 simultaneously? I don't know enough about cloud technology. I can tell you if I was buying a laptop any time in the past 20 years, I'd much rather buy one a year for 3 years than buy all 3 in 1 year and 3 years later have all of them be obsolete. Maybe that's not true for the cloud. Maybe that's too simplistic, but you might learn something on the first one that would inform your bid for the second one. If not, the second runner-up would get the bid 2 years later or a year later.
So the short answer is, I think one of the things that we hope to have happen, and again, because this is envisioned as a consortium, is to have these groups playing, in effect, having what each of the individual groups do, have them interact with each other and do better things. Again, I'll go back to Lincoln's analogy of the early days of Internet protocol, the early days of the web. What you had were a bunch of groups proceeding along a variety of different paths that when they would create new capabilities, they'd get it coded, it could then be brought in as a broader capability. And I think by doing them at the same time, we get a synergy that we wouldn't get if we started one and then we stopped and evaluated and started another and stopped and evaluated. I see your point, but I think it's going to behave in a slightly different way, because it's more like we've got three people that are all trying to decide, now what's a laptop and how are we going to build one?
Yeah, I'm sure this is going to evolve in ways we can't anticipate. Seems like it's time to get started.
I just want to say that we're not building three different labs. We're building, a laptop, a mini computer, a supercomputer, because different parts of the community will need dramatically different tools to address that question. For instance, people do imaging, people that will use, for instance, mutational data to do structure prediction and understand how those mutations are implemented on protein structure. People that will do genomic data will use dramatically different expertise. So I think having one single solution is going to be very, very hard.
Okay, is there Jennifer?
I don't want to lose this point that Bill made. I mean, given the flexibility here, why wouldn't we want to, we've talked all about business partners and everything at the NCI, why wouldn't we want to take advantage of open competition, but then also just go to people who built these clouds and kind of go head to head with that in terms of trying to, because I agree you're going to learn a lot in this whole space, and maybe we have a lot to learn from people who've already put a huge investment in, back to your point, but we only have so much money. So why wouldn't we go both places?
We've gone to people, Amazon, Google, and they're like, they have a model that works by charging for bandwidth and storage. And the problem is that it is essentially completely out of scale. Right now, the computation that we can accomplish at individual site, academic sites, is about 1/10 the cost that it would take the corresponding Google and Amazon model. And by the way, it is a little bit of a misinformation that Amazon has or Google may have bigger clouds than some of the academic sites. Some of the academic sites have very, very big clouds, and they provide them at cost recovery level.
But presumably there's nothing to preclude an applicant
absolutely.
in working with some of those service providers. Charles Sawyers.
So just on that point a little bit, so I'm on the organizing committee of the Alliance, as Harold mentioned, and we're still trying to figure out exactly what's going to happen. But there are some ex-Google, ex-Facebook, ex-Amazon people who have enough money to now either lead a life of leisure, as I think someone mentioned, or actually do something really interesting. And I think those are going to be highly incentivized, these people. I think they're already working closely. David Hausler is really driving up the energy level over there on that coast. So I wanted to, George, make sure that, I don't know if you can reach out to people before an official announcement, but it would be great to time this with ongoing discussions at the organizing committee.
Sorry, I wanted to say one thing about the academic clouds. It means they have to support user access. So if you're going to do it this way, fine. Just make the pilot, hold the pilot projects accountable to supporting 10,000 users a month. So, and that their network is robust to user requests. This is the advantage of some of the large-scale
well, and
centers.
Actually, in point of fact, one of the key there are a few mandatory requirements, but I mean, one of the things we're anticipating is that they have to be able to make the cloud available. Whoever is going to respond is going to have to be able to make the cloud available to people outside their institution.
I mean, that has to be demonstrated during the pilot phase.
Yes, absolutely.
Okay, I think it's time. Is there a motion? Move second. Any further discussion? All in favor?